Welcome to this video on a few preliminaries, foundations that we need for calculus, that we will be needing for the future videos. So what we will be talking about is numbers, collections of numbers, a few notes on how to solve inequalities, and a few remarks on straight lines. So let's look at the outline for this video. As I said, numbers and intervals, so the different types of numbers we have, like natural numbers and fractions and things like square root of 2. Then how can we solve inequalities of different types? And a bit on straight lines, and I'll wrap up with a short summary of what we have seen in the video. So let's see. First, we have the natural numbers. And they are the numbers that we use for counting. So 1, 2, 3, and so on. And it is always a bit of discussion whether 0 is also a natural number, but let's include it there. So 0, 1, 2, 3, 4, those are the natural numbers. Now, an extension of those is if we include also the negative version of them. So then we get the integers or the whole numbers. So then we have the natural numbers 0, 1, 2, plus, minus 1, minus 2, and so on. Now, you see the symbols here on the slide. So these are the symbols if you type them. If you would write these collections, then for the natural numbers, we do a capital N with a double bar on the left. And for the integers, we do a Z symbol, and also we make this one double. So that is if you handwrite these collections, if you should ever want to do that, you do it like this. You may be wondering why the integers are denoted by a Z. Well, that's from the German word Zahlen. Also the English word integer, you would get capital I, and that's not a very clear symbol for this collection. So Z is the symbol that is always being used in mathematics. Now, once you start doing stuff with these numbers, you soon realize that if you divide two numbers, you get something that is not in these collections yet. So if you have 3 apples and you have 4 people, you get 3 over 4 per person, and that's not in this collection. So that naturally leads us to the rational numbers, which are denoted by Q for quotient. And again, if you handwrite that, you would write something like a Q with an extra bar in there. So you also get a double bar. So let's see, how is this collection Q defined? So it is quotients of the form P over Q, where P and Q are integers. But of course, we cannot divide by 0. So the only restriction is that Q should not be equal to 0. So here you see a couple of examples. A half, 1 over 3, minus 3 over 4, 1 over 6, or this strange number here. And they are all rational numbers, quotients. What is interesting, if you look at the decimal expansion, so if you punch them in on a calculator or your computer, whatever, you see that this decimal representation for at least the examples that I have here, they all terminate. Like here, it's 0.5 and the rest are zeros. And here, minus 0.75 and then we get zeros. Or they repeat themselves. Like 1 over 3, we have 0.3 and then the 3's keep on repeating. And the strange number that I constructed here, if you would look at it, you would have this expansion here. So the decimal expansion either ends or repeats for these quotients, these rational numbers. And you may be wondering if we now have all of the numbers that we would like to work with, and that is not true. And basically the numbers that we lack are the numbers that have a decimal expansion that does not repeat. And you already know examples of those numbers. So for instance, the square root of 2, or pi, or e, so 2.71 and so on, that we will all encounter in future videos. They are called irrational numbers or real numbers. So Q does not have all the numbers. These special numbers that have a decimal expansion that does not repeat itself or does not terminate are called irrational ones. And if we put all the numbers together, rational and irrational numbers, we have r. And again, if you would write this by hand, you would write it like this, so with a double bar on the left. Now here I have plotted the real axis, so just a straight line, that contains all the numbers that you know. So here are a couple special ones. So we have 0, 1, 2, -1, -2. They're all integers. Then we have fractions like -3/2 and a half here. And also there is the irrational numbers, or a couple of them here. So there is square root of 2, and there is pi. And of course there are many more numbers. So all the numbers that you know, that you normally work with, that is the collection R. And what you can also do is we sometimes, so just a bit of notation that I will frequently use, but let me introduce it for when you haven't seen it yet. You can write something like 2 is an element of n. So this little euro-like symbol, if you like, means is an element of. So it means that 2 is in the collection of natural numbers. And similarly, a half is an element of Q, or a half is also an element of R, if you like. To denote that something is not an element of a collection, so for instance, a half is not an element of z, so half is not an integer, we have the same symbol, but we strike it. And then finally, now for notation, you will probably see that I have expanded on the numbers. So I started with the natural numbers. I included the negative ones, so I just added to the natural numbers to get the integers. And then I added the quotients, and then I added the irrational numbers. And to denote that, you can also write that n is a subset of z, is a subset of q, is a subset of r. So this symbol means is a subset of. So that is also something that we will be using sometimes. Let's see, that concludes it for now, I think. Most often we will be working with real numbers. So in many of the applications, when we start doing stuff with functions and so on, we will be using the real numbers. So that's the most important collection of numbers that we will be using. Now, to have subsets of real numbers, we often work with intervals. So here, what we have, this notation here, so I have square brackets and then two numbers a and b. What this means, let's first look at the picture here. So it is a part of the real axis. It is all the numbers in between a and b. And because here those endpoints are filled circles, it means that a and b are also in the collection. Similarly, we have an open interval here. So if we have normal brackets, round brackets, then we get the interval from a to b. But now, since we use round brackets, it means that the endpoints are not included. So here is a little open circle, including that, meaning that a and b are not in the collection. So this is all the numbers in between a and b, but not a and b themselves. And here I have also written that as a set. So here what it means, so the curly brackets here, these two, they denote that we are constructing a set of numbers. So sets are usually in between the curly brackets. And then this means we take every real number, and then the vertical bar imposes a condition on the numbers. So we take every real number x, and I always read this aloud as for which. So it means for which the following condition holds, and then the condition that we impose is that x is larger or equal a and is less or equal b. So that is the way you can denote that. And then here, if you look at the open interval, you see that I impose the condition a less than x less than b. So that means every x in between a and b. So similarly, you can also talk about half open or half closed interval. So this means that a is not in the set and b is. So if you like, this here is the set of every real number x for which a is less than x is less or equal b. And similarly, this collection here. So now you see that the square bracket is with the a. So this equals every real number for which a is less or equal x is less than b. And then finally, that's the last bullet here. We can also talk about unbounded intervals. So from minus infinity up to a. And then a can be included or a cannot be included. And this is every number basically to the right of a. And since there is a square bracket here, a is included. And here we have every number to the right of a, and a is not included. Note that infinity and minus infinity are not numbers. So they are never included. So if you write down infinity, it automatically means that you will have a round bracket there, because infinity cannot be in the interval. And similarly, minus infinity also has a round bracket. Okay. Now, the next bit that I would like to talk about is about inequalities. And I'm first going to do a couple of examples how you can solve inequalities. And this is something that we will frequently need in what comes later. So let's go to a blank slide. And I am first going to consider a little example where I'm going to solve the inequality 2x plus 5 is less than 13. So this is not very difficult. What you do to solve it is first you subtract 5 from both sides of the equation. So then you get 2x is less than 8. And then you divide the equation by 2 and you find x is less than 4. And now we know all the solutions. So the solutions are, so the set of solutions is minus infinity up to 4, and 4 is not included, so we get a round bracket there. Next example, a little bit more difficult. This was an easy one to get going. So example. So now I'm going to solve 6 is less than 1 minus 3x less or equal 10. So we proceed in the same way. In the middle here, the 1 minus 3x, I want the 1 to be gone. So on all sides of the equation, I subtract 1, which means I get 5 is less than minus 3x is less or equal 9. Now I'm going to divide the equation by minus 3. And you should remember that if you divide or multiply an inequality with a negative number, like minus 3 is, then the sign changes. So then we get 5 divided by minus 3 is bigger, because we have a negative number. X is larger or equal 9 over minus 3, that's minus 3. And now let's swap the equation that it looks like a normal equation. So I put the minus 3 here, less or equal x, less than minus 5 over 3. And then we're basically done, because now we know that the set of solutions, so all solutions of this inequality, or two inequalities if you like, are the interval from minus 3 up to minus 5 over 3. And this side should be open because we have a strict inequality there. Now let's make it a little more challenging even. I'm going to look at an inequality where we have a fraction. So let me get some fresh paper. So third example. Let's look at the inequality x minus 1 over x plus 2 is larger equal 0. Now, it would be tempting to multiply the equation with x plus 2. But that is not the way to proceed. And the reason is that we do not know whether x plus 2 is a positive or a negative number, so which sign we should keep track of. And then we can make case distinctions, but that's going to give headaches very, very quickly. So what we do here is we make a sign chart. So what we do is first we look where the numerator and denominator are 0. So let's see the numerator. X minus 1 is 0 for x equals 1. The denominator x plus 2 equals 0 for x equals minus 2. And now I'm going to make a sign chart. So what is that? A sign chart means that I'm going to draw the real axis. Below I'm going to put x, and up here I'm going to put the sign of the expression we're interested in, x minus 1 over x plus 2 here. And I am going to label the special x values, so minus 2 and 1. I know that the expression we're interested in, that it equals 0 when x equals 1. So let's put that in here. So here it is 0. For minus 2 we have division by 0, so I'm going to put a question mark there because it's not defined. And now the main idea is I'm interested in whether this thing is positive or negative. And in between these special points, it has to keep the same value. So that means for all values in between minus 2 and plus 1, it is either plus or minus. And I have to find out what it is. But it cannot change sign there. It can only change sign at zeros or points where it is not defined. Similarly, for every value larger than 1, it is also going to be positive or negative. And also in this region, it is either going to be positive or negative, but it cannot change sign anymore. Now to find out whether I should write here plus, plus, minus or whatever, what I'm going to do is I'm going to pick a value there and check the sign for what it is. So for instance, if I want to know to the right of 1, so this region here, is it going to be plus or minus? I can pick any number bigger than 1. So I'm going to pick a convenient one, which is 1000. Because if I pick 1000, I immediately see that this is positive. That's 1000 minus 1, that's 999, which is positive. This is also positive, so I get plus over plus, which means that I can write a plus sign here. Now here, in between minus 2 and plus 1, there is 0. So I'm going to check which sign the expression has for 0. Up here I find 0 minus 1, that's negative. So this one is going to be negative for x equals 0. This one is positive for x equals 0. If I have a negative number that I divide by a positive number, I am going to find minus. And then finally, if I want to know in this region, should I put a plus or a minus, I'm going to take minus 1000. And I find that this is negative, so I have negative over negative together gives a plus sign. So then I have plus, minus, plus. And now this sign chart, I can simply read off the solution now. Because the question is, when is this expression larger equal 0? Well, here it is 0, here it is positive, and here it's positive. So I can now read off the solution. x is less than -2 or x is bigger equal 1. And if you want to write that in terms of intervals, then I have a set of solutions. So from -infinity up to -2. -2 is not included. And then union 1 to infinity, and 1 is included. And here I have used a symbol that you may not have seen before. This means union. And it means that I simply combine the two collections. So I have a bag of numbers, I have a second bag of numbers, I put them all together into a new bag. That's what it means. Okay. So let's do one more of these inequalities with fractions, but a little bit more difficult even now. So let's get some space. So what I'm going to do, example. So I'm now going to solve 6 divided by x minus 3 is less or equal 3 over x minus 5. So again, you might be tempted to multiply the inequality with x minus 3 or with x minus 5 or with both of these numbers, but we don't know whether they're positive or negative. So that's going to give us a headache. So let's not do that. So I'm going to move everything to the left side of the inequality. So 6 over x minus 3 minus 3 over x minus 5 is less or equal 0. I'm going to give them the same numerator. So 6 times x minus 5 minus 3 times x minus 3 divided by x minus 3, x minus 5 less or equal 0. Then I can simplify this a little bit. So here I have 6 times x and I find minus 3 times x. So I have left 3x. I have 6 times minus 5, that's minus 30. Minus 3 times minus 3, that's plus 9. So I am left with minus 21. X minus 3, x minus 5 less or equal 0. And if you like, you can write that as 3 times x minus 7 over x minus 3, x minus 5 less or equal 0. So this was the preparation phase, if you like. Now we make a sign chart, and then from the sign chart we read off what it should be. Now I can squeeze the sign chart on this slide, I think, without making it too cramped. So here I put 3 times x minus 7, x minus 3, x minus 5, the expression we're interested in. Below I put x. I now have 3 special values. I have 3, 5, and 7. For 7, I know the expression is going to be 0. For 3 and 5, I have division by 0, so it's undefined, and I put question marks. And then I have to plug in special numbers. So to find out the sign in this region for numbers of x bigger than 7, I'm going to plug in 1000, and you immediately see that we get plus over plus times plus, so everything's going to be positive, so this is going to be positive here. To find out what is happening in between 5 and 7, I could take 6. And for 6, that is in between, you see that I get a minus sign here, and here I get a plus, and here I get a plus. So the whole expression is going to be negative. In this region, I can take 4. And if I plug in 4, you see that I get minus, plus, minus. So the whole expression is going to be positive. And to the left of 3, I can plug in minus 1000, and I have negative divided by negative times negative. So that means that the whole expression is going to be negative. So we can immediately see that the set of solutions, I have either minus infinity to 3, and 3 is not included, union with the interval from 5 to 7, and I have less or equal, so equal to 0 is also allowed. So what I have here is 5 to 7. So that solves this inequality. Now finally, one more example of an inequality of a bit of a different type, not so difficult. What is called a polynomial inequality, and this term will become clear in a future video why this is called like this. So if you have x squared plus x minus 6 bigger than 0, so what you do here is you also will be using a sign chart. So I'm going to write this as x plus 3 x minus 2 bigger than 0. I'm going to make a sign chart. Here I put x, up here I put x squared plus x minus 6. So we see that for minus 3 and 2, the expression is going to be 0. To know what sign it has for values bigger than 2, so here in this region, should I put a plus or a minus? I'm going to pick 1000 and I get plus times plus. So I know that I have a plus here. In this region, that's also easy. I'm going to pick minus 1000 and I get negative times negative together. It's going to be plus again. And then in between minus 3 and 2, I can pick x equals 0. And for 0, I find 3 times minus 2. So that is going to be negative. And now I can read of the solution. So the set of solutions, I want positive, so that means that I have to take the interval from minus infinity to minus 3. Minus 3 is not a part because the expression needs to be strictly positive, not 0. Union with 2 to infinity. So that concludes a couple of examples of inequalities. Now, let's see what we actually used while we were doing this. So that is formulated as a theorem here, but I first wanted to show you some examples that you know what the theorem is about, what it really says. So here is a theorem, and let's go through it line by line. And here in black, I put the interpretation of what this formula says. So rules for working with inequalities, basically a kind of justification of what we have just been doing. So let's see. We pick 4 numbers, A, B, C, D. And here it says if A is less than B, then also A plus C is less than B plus C. So if you have an inequality, on both sides of the inequality, you can add a number or subtract a number, right? I mean, if C is a negative number, you're subtracting a number here. Then if A is less than B and C is less than D, then you can add the inequalities together. So that's what it says in black. Then we have that a plus c, so the left sides together is less than the sum of the right sides, b plus d. And then finally, if you have an inequality, you can multiply it with a positive number. If you multiply with a negative number, the inequality sign changes. So we go here from less to bigger. And we already used that. Then we have also seen if you have inequalities with fractions there. So for instance, x plus 3 over x minus 2. The way to go is to find the zeros of the numerator, of the denominator, and then make a sign chart. So the next topic is absolute value. The absolute value function, you already know that. If you have a value of x that's bigger or equal to 0, then you simply return x. And if you have a negative number, it becomes minus x. So the absolute value of 3 equals 3. The absolute value of minus 7 equals 7. And then if you plot the graph, you get basically the function y equals x, straight line with 45-degree angle with the positive x-axis. And for negative numbers, you get y equals minus x. Basically, the absolute value of x is the distance of x to the origin, to x equals 0. And as it is a distance, you know that it's always going to be larger equals 0. So for x is 0, the absolute value of 0 equals 0. And as soon as x is unequal to 0, it's going to be a positive number. Now, a few remarks. First, if you have the absolute value of a product, so if you multiply a and b, then you can also multiply the absolute values. And the absolute value of a plus b is less or equal the absolute value of a plus the absolute value of b. That's called the triangle inequality. And basically what it says is if you... Let's forget about this interpretation. That will become clear if we talk about vectors. Then I will get back to this, but let's leave that for now. And the third bullet here says that if you pick some positive number, then absolute value of x is less than r. You can rewrite that, and that's maybe easier to work with, to minus r less than x less than r. So as a little example, if you have the inequality, so example, if you have the inequality x plus 4 is less or equal 7. So what that means, that's the same as minus 7 less or equal x plus 4 less or equal 7. And now we're back to what we have already seen before, so we can subtract 4 and we get minus 11 less or equal x less or equal 3. So the set of solutions is the interval from minus 11 up to 3, and both of the endpoints are included. A bit more difficult, that's an example that I put on the slide. If you see an inequality like this, that can seem very hard to work with. And actually there is a website where you can ask mathematical questions. And this is one of the questions that was posed there, and it raised quite a bit of discussion. So the way to solve this is basically what we've already seen. So first we move everything to one side of the equation. So we get a 0 in the right-hand side. Then first we are going to consider the equation where we put equal to 0. So if we have that the expression equals 0, it means that the two of them are equal. So it means that 5x minus 4 equals plus 3x minus 4 or minus 3x minus 4. And then we're back to the simplest situation. So this means that either 2x equals 0 or 8 times x equals 8. So we find two possible solutions, 0 and 1. And just to be sure, if you have never seen this symbol before, it means or. So it's just a mathematical notation for either this holds or that holds. Or maybe both of them can be true. So now we make a sign chart like we have done before in this video. So I put 0 and 1. Those are the special values for x. Up here I put the expression we're interested in. Well, that equals 0 for these. I plug in intermediate values and see what the sign is. So apparently we get plus, minus, plus. We had to solve this inequality, so I have to check where it is negative. So apparently x values in between 0 and 1 are the ones that we are interested in. So the solution is 0 less than x less than 1, or if you want to write it as an interval, it's the interval 0, 1, and the endpoints are not included. So we are doing kind of different bits here, preliminaries. One more is the distance between 2 points. That's not very difficult, but we will be using that extensively. If you take 2 points in the plane, so I have a point P and a point Q, then this is the formula for the distance. And that is very easy to see, because if you plot it, so P here has coordinates x1, y1. The point Q here has coordinates x2 and y2. And you see that if you draw a little triangle here, you can apply the Pythagoras theorem to find the length d, and that is precisely the distance between P and Q. And Pythagoras tells you that this holds. Note also that the order of the points is not important. I could also write this as x1 minus x2 squared plus y1 minus y2 squared equals d squared. And of course the distance between P and Q is the same as the distance between Q and P. So the order of the points doesn't matter. So this is getting to be quite a long video. Let me go to the last item on the agenda. So a few notes on straight lines. You know that if you take 2 points in the plane, so here again P and Q, that there is precisely one line that goes through both points. To find the equation for that line, we first look at the slope. So the slope m is the distance in vertical direction divided by the distance in horizontal direction, delta y over delta x. So that's y2 minus y1 over x2 minus x1. And that tells you the slope of the line. So if it is positive, the line goes up. If it is 0, you have a horizontal line. If it is negative, the line goes down. If m is bigger and positive, it goes up faster, and so on. The general equation for a straight line is y equals mx plus b. M is the slope and b is the y value for x equals 0. So that's where the straight line intersects the vertical axis, the y-axis. And if you are asked for a line that goes through a point and you have the point plus the slope, so that's a little bit different. Now we do not have 2 points, but we have other data. Then you can use this equation. You can still use this equation, you'll find the same one. But this is a little bit easier. You see, if you plug in x equals x1, then the right side here becomes 0, and you see that y should equal y1. So that's a bit of a shortcut here. So let's see. So the only thing that I wanted to add is if you have a straight line, so x-axis, y-axis, If your line goes up like this, so let's say that this is the line, then you know that the slope is positive. If you have a line that goes down like this, you know that m is negative. And if you have a horizontal line like this, this means that m, the slope, equals 0. If you have a vertical line, then the slope is undefined, because a vertical line has equation x is 0, x is 1, x is 10, whatever, and y is not in there, so there is no slope in there. So let me also add that here, maybe. So if you have a vertical line like this, then m is undefined. So then there is no slope. Now finally, two lines are parallel. So if you have one line, and let me see, let this be my second line for a sec. So I have two lines. If they are parallel, it means that they have the same slope. So that is still on this slide. So two lines are parallel if they have the same slope. What you could also think about is when you have two lines that make a 90-degree angle, then there is also a relation between the slopes. And if you think a little bit about that, so if you have, for instance, x, y, and if I would plot here the line y equals x, then you know that this line here, y equals minus x, that makes a 90-degree angle. And then you might be tempted to take, if you have slope 1 here, slope minus 1 here, you might think that you have m and minus m as a relation between the two slopes. That is not true, because if we look at the example, it's always easy to have simple examples. So if we look at the line, say that this is the line y equals 2x, then you see that the line that is perpendicular to that, well, it starts doing a little bit like this, right? And if you think about that a little bit longer, then you will see that the line that makes a 90-degree angle has the equation minus 1/2 times x. And the relation between the two slopes is that m1 times m2 equals minus 1. So m1 is the slope of the red line, m2 is the slope of the green line, and then their product should be minus 1. So that is the last bit that is on this slide. m1 times m2 equals minus 1. And always think of these simple examples where you can easily see that. So let's wrap up this video and see what we have seen. We have introduced numbers, natural numbers, integers, rational numbers, real numbers, and especially real numbers is what we will be working with. We have solved inequalities, and we have seen that sign charts are a great way to do that. And then we did a little recap of straight lines. So this has been quite a long video. I'll try to make them shorter in the next couple of videos. I hope it was all clear. Let me know if you have questions, or if everything was clear. I also like to know that. And I'll see you in the next one.